Antiderivatives and areas. So the first thing I want to recall is the area of the rectangle. Area of rectangle, the formula is length times width. The area of the triangle is 1/2 base times height. One half base times height. What do we have here? What else we have to know? We have to deal with rate, distance, time problems. We know that distance is rate times time. That's how we find the distance. So if we want to look at it graphically, so let's say if the time is 1 hour and the rate, let's say the rate is 10 miles per hour. If you go for 1 hour, you will cover 10 miles, right? That's the distance, 10 miles. So graphically, if I put this to be the time axis for the time, and this is the rate R, we said 1 hour, say 1 hour, and the rate is 10 miles per hour. This is the 10 miles. So the 10 miles will be represented by this area. This is the distance. How about if you go 2 hours? So 2 hours means you move to the right twice, 2 hours, with the same rate, you got another 10 miles. So the total area will be 10 plus 10. So D would be 20 miles. See, I'm using graphs to show you how to find distances. In general, how about if we have a graph of a function that goes this way, call it f, and we would like to find the area under this graph, or approximate the area under the graph. So what do we do to do that? It depends what you want to do. One way to approach it is finding or using rectangles. Let's say I want to start from the left side. So this is left endpoint is called. And I want to draw a rectangle. So you draw a rectangle with width dx. So the width of each rectangle I'm going to draw is delta x. Delta x. So how does that work? So assume that's delta x. So you go all the way up till you hit the curve, and then you go the same width, and then down. Same width again, and down. Whatever hits this, same width again, down. Same width again, down. Same width again, down. That's the each rectangle has a width delta x. Each rectangle, they all have to have the same width. Now the area under the curve is approximately the sum of the areas of all rectangles. And to see how to work that out, let's call the first x is x1, then x2, then x3, then x4, then x5, then x6, x7. So I'm going to find the area of each one of these rectangles and add them up. So how do you find the area of a rectangle? We said it's length times width. We know the width is delta x. How do I find the length of the rectangle? How do I find this? Well, remember this is a function f. If I find f of x1, so if I take x1, evaluate the function at that, that will give me the distance from here to there. That gives me the height or the length of the rectangle. If I want to find it for the next one, I find f of x2. Next one, f of x3, all the way to this, which will be f of x6. So x7 doesn't count. We don't need to count it. So for the first rectangle, we say f of x1 times delta x. How many rectangles we have? 1, 2, 3, 4, 5, 6. 6 rectangles. So f of x2 times delta x. F of x3 times delta x. F of x4 times delta x. F of x5 times delta x. F of x6 times delta x. And this will be called L sub n. L for left endpoint, because we start from the left side. You could start from the right, but I start from the left. So when you start with the left, we skip the last point. As you can see, x to the 7 was not used. I'm going to show you an example how to work this out. Given the function y equals f of x equals 1 over x squared, and we need to find the area under the curve from 1 to 7, from x equals 1 to x equals 7. So how do we do so? If you try to graph the function, the graph goes this way. From 1 to 7, we're going to take the width to be 1 for now. So delta x, I'm going to assume it's 1. So it's going to go 1, 2, 3, 4, 5, 6, and 7. Down this way, wherever across the graph this way, wherever across the graph this way, this way. So we need to find the area of all these rectangles, which will give me an approximation of the area under the curve from 1 to 7. So how did we do it earlier? The area, we say, is about f of x1 times delta x plus f of x2 times delta x, plus all the way, it's going to go all the way to f of x6, not the last one, just up to the one before the last one. And in this case, x1 is 1, delta x, x2 is 2, delta x, f of 3, delta x, f of 4, delta x, f of 5, delta x, f of 6, delta x. And delta x is 1. So all we have to do, remember f of x, let me rewrite it, is 1 over x squared. So f of 1 would be 1 over 1 squared times 1, 1 over 2 squared times 1, 1 over 3 squared times 1, 1 over 4 squared times 1, 1 over 5 squared times 1, 1 over 6 squared times 1. And this would be 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25 plus 1 over 36. If you put that into the calculator, that gives me 1.4914. That's the approximated area from 1 to 7 under that curve y equals 1 over x squared. in general, how this works, why did I take delta x to be 1? Can it be different? Yes, it could be decimal, could be fraction, could be any number. We decide based on if you have an interval a to b, and we need to split it into n sub-intervals. Then the width of each rectangle is given by b minus a over n. That's delta x. That's how we calculate it. So you have to decide how many rectangles you want, or it's given in the problem. Another form can happen is they can give you a graph and they ask you to find the area. So they graph it for you. So let's say they ask us to approximate the area under the graph of f of x equals x squared plus 1 over the interval 0 to 5 by computing the area of each rectangle, and then adding. Adding means adding all the areas of these rectangles. So I'm gonna show you what is given. They give us the graph here, say like this. This is the graph of the function f, and goes 1, 2, 3, 4, goes this way. This is given. All the way to 5. And the area that they they want us to do is the area for all these rectangles, as you can see, the shaded rectangles. So all this is given. So we just have to find the area and add them up. Okay, we do it the same way we did the other ones. So the area is going to be f of the first point is 0 delta x plus f of 1 delta x plus f of 2 delta x plus f of 3 delta x, and the last one f of 4 delta x. We don't touch the last one. So then f of 0, if you substitute the 0 back into the function, because f of x is x squared plus 1, put 0 and you got 1 times delta x. Delta x here, you see it's the width of each rectangle, which is 1, right? So it's 1 plus f of 1, it's 1 squared plus 1, 1 plus 1, 2 times 1, 2 squared 4 plus 1, 5 times 1, 3 squared 9 plus 1, 10 times 1, 4 squared 16 plus 1, 17 times 1. So that gives us 1 plus 2 plus 5 plus 10 plus 17. And if you add them up, I got 35. We can take the same function, and but I'm gonna split it into, assuming delta x is different. Let delta x be 0.5, a half instead of 1. Okay, a half. And we want to go, let's say 0 to 7 over the interval 0 to 7. So it's gonna be the same graph as before. It's just the interval changed and the width of the intervals changed. So it goes this way. This is f of x, and that's the 0. So you want to go by an increment of a half. So you're gonna go a little bit this way down, this way up, this way, this way, this way, this way, this way, this way, 0.1, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, 5. There's more to do. Oops. 5.5, 6. Two more to go. 6.5 and 7. So that's what we have, and then you have to find the area under all these rectangles. So again, delta x is 0.5, and the function is still the same, x squared plus 1. I highly recommend you guys try it now on your own. So if we go through the calculations, we start by saying the area under the curve equals, or we're looking for, is f of 0 delta x plus f of 0.5 delta x plus f of 1 delta x, all the way till the one before the last one, which is 6.5 delta x. And notice something you can do. You can take delta x out, which is 0.5, and you don't have to do it with every single one of them. You can just keep it outside at all times and do the work inside for the function. 0.5, f of 0, it's 0 squared plus 1, 0.5 squared plus 1, 1 squared plus 1, 0.5 squared plus 1. And all you have to do is substitute those into the function that you see, x squared plus 1. So first, the way you do it is you calculate this. This is 1. This is 0.25, so 1.25, etc. all the way. And then substitute them into the function. Whatever number you get here. I got 218.75, and multiply them out. 109.375. That's the approximated area under the curve. Now we can look at more stuff, such as back to the antiderivative, f of x dx. You know, we call this antiderivative of f of x from the previous section. Now what happens, I want to get this integrated into this section lesson. So say this is f. If I'm trying to find the area from A to B under the curve, like this area, the way we represent it using integral, we say the integral of f x dx from x equals A to x equals B. And then we say that's the antiderivative of f(x) from x equals A to x equals B. X equals A to x equals B. So again, this represents the area under the curve of f of x from x equals A to x equals B. That's what this stands for. It's just a notation that was found by a German mathematician. His name Riemann. He was the one who found it and applied it to find areas. And this gives actually the exact area under the curve, not the approximated area, but the exact area under the curve. And I'm going to show you how to apply this. Let's say for dx, x equals 1 to 3. We need to find what that is. So we're going to do it using geometry or geometry method. So how do we do this one? Let's say I want to represent it on the graph, x, y, like so. So we draw, this is the function y equals 4. So you go 1, 2, 3, 4. So it's a straight line, horizontal line, y equals 4. And then we're going to go from x equals 1, x equals 1 to x equals 3. So it's going to be this area. That's what this integral represents. Graphically, That's what it represents, the area of this shaded region. So this again is basically the area of the yellow region on the right side, and that yellow region is basically the area of a rectangle. And what's the area of the rectangle? Is length times width. What's the length here? It's 0 to 4, that's 4 units, and the width is 2 units from 1 to 3. So that is 8. So the integral that you see in blue up there in the upper left corner, that's 8. That's 8. We can look at another example, 4x dx from 0 to 5. We're going to do this graphically. How do we use the geometry to calculate this? That's what we're going to do. The first thing again to do is to graph the function, whatever function we have in there. Okay, the function. So we need to graph y equals 4x. If x is 0, y 0, x1, y 4. Like that. So it goes from 0 to 5. Say 5 is here. 0 to 5. So that would be this this region here. Zero to 5. So how do you find this? This is basically this represents the area of the yellow triangle, to the right. And how do you find the area of the triangle? We do 1/2 base times height. Now where's the base? The base is from this part from here to here. That's the base, which is 5 units. And the height, where's the height? The height is this part, the one I'm highlighting in blue, where the 5 is. That's the height. So how do I find the height? Well, remember the function f of x that we have is 4x. To find the height, you simply find f of 5. What is f of 5? You replace x with 5, and that's 20. So this height is 20. The height is 20, so that's what goes in here. So if you multiply this out, 1/2 of 100, so the answer is 50. So the area, or that integral, is basically exactly equals to 50. That's the exact area under the curve. Another example, 0 to 3, x plus 1 dx, the integral from 0 to 3. Can go over it now. So we're going to graph y equals f of x equals x plus 1. We're going to graph this one, xy, x0, y1. If you take y0, x negative 1. So it goes from 0 to 3. 0 to 3. So how do you find the area? So this figure from 0 to 3, it's a trapezoid. There are many ways to find the area of the trapezoid. You need it later on for later sections. I can give you the formula. The area is 1/2 base 1 plus base 2 times the height. Where's base 1? This piece here is base 1. This is base 2. And this is the height of the trapezoid. So base 1, notice you can see base 1 right away, it's 1. The height is 3 units. To find base 2, we find base 2 is basically f of 3. Substitute 3 into the function. 3 plus 1 is 4. So this is 4. So I got all the numbers in. Base 1 is 1. Base 2 is 4. And the height is 3. That's 1/2 of 5 times 3. 5 times 3, 15. Half of it is 7.5. That's one way to do it. The other way, you can drop a height this way. This is 1. This is 3 units because the whole thing is 4. So what we can do, we can say the area is the area of the rectangle that you see plus the area of this triangle. So what's the area of the rectangle? Is 3 times 1. The area of the triangle 1/2, base is 3 and height is 3. So that gives us a 3 here plus 1/2 of 9. 1/2 of 9 is 4.5. And 4.5 plus 3 is 7.5.